Now we will look at the Vapnik-Chervonenkis dimension. This gives us a way to measure the complexity of the model. Remember, the complexity of the model determines the performance or the cost on both the training and the test sets. There are various techniques to determine bounds on the generalization error on the test set. A good treatment of this is given in the reference in the instructor's notes. Let us now look at the following expression. This shows that the error calculated on the test set has an upper bound. We can quantify a degree of belief in this upper bound using a parameter eta such that given eta, for example 0.01, we have a probability of 99% that the test error is bounded above by the expression inside the radical. Also notice the expression inside the radical depends on the quantity h. This quantity h quantifies the complexity of the model. Let's look at the following diagram. In this diagram, we are increasing the complexity of the model as we go along the horizontal axis. The cost calculated on each of the dataset is on the vertical axis. Now, if you look at the training term, which is the training error here, you will have a curve like this. Looking at the term under the radical sign here is the complexity term that increases like that. So you see, the test error is upper bounded by this red curve. At some point, we can select the minimum of the test error, which is something over here. If we fix the sample size n and the training set error is given, then we see that the expression here depends on the quantity h, which we have already introduced as the VC dimension. There are various ways one can calculate the VC dimension, and the topic is covered in detail in the references in the instructor's notes. For general models, calculating the VC dimension is a challenging problem. However, for linear classifier models with m dimensions or variables or features, we have a very simple expressions. The VC dimension is given as h, which is simply m plus 1.